Hello, my name is Fiona Thorburn and I'm a Research Associate in the Single Photon group at Heriot-Watt University. I'll be presenting a summary of the work related to germanium and silicon single photon detectors, which has been carried out between Heriot-Watt and the University of Glasgow. A single photon detector is a device that can precisely measure the arrival of a single photon of light, and there are many important applications for this type of device shown here on the bottom of this slide. For instance, you can send out a pulse of light and measure how long it takes for a photon to return to your sensor, and thus you can calculate how far away the reflecting object is. So autonomous vehicles could use this technology to build up 3D maps of the surrounding environment, allowing them to navigate safely even through obscurance such as smoke, fog and rain. However, the main problem with the current technology is that it works at relatively low maximum count rates, is quite expensive and lacks compatibility with CMOS fabrication. One of the main types of detector that is currently used for these types of applications is called a single photon avalanche diode or SPAD detector. The working principle of such a device is shown in this animation here. When a SPAD absorbs a photon, it generates an electron-hole pair that can initiate a cascade or avalanche of more electrons, and then we can measure this avalanche as macroscopic current. Silicon CMOS SPADs are widely available in retail products today, for example mobile phones, but at longer wavelengths in the shortwave infrared, alternative narrower bandgap materials must be used, and these materials, for example indium gallium arsenide, are much more expensive in comparison. In Quantic, we are replacing these expensive materials used in this current technology with alternative materials that allow devices to be made much more cheaply because they can be made using the existing silicon foundries that are used to make computer chips and camera sensors. This is achieved by the use of germanium on silicon material platform. In Quantic, we have redesigned the germanium on silicon SPAD device with a planar design. That means there is significantly less chance that the device produces a false count, which occurs when a current pulse is emitted when there is no light incident on the device and is also known as a dark count. You can see by looking at these electric field simulations in each device that the old device on the left-hand side, there are these hotspots which increase the probability of these dark counts. You can see the improvement also when you look at the noise equivalent power. This is a figure of merit indicating how sensitive a SPAD is, with a lower number indicating higher sensitivity. You can see that moving to the new design, planar design compared to the old MESA design, has made the device significantly more sensitive. The developments and improvements made on these detectors has enabled new Innovate UK projects in collaboration with a number of industrial partners, which are shown in the bottom half of this slide. These two projects, Aquasec and SPIDER, address the two major applications introduced on slide 1, namely unbreakable encryption and 3D mapping technology, which is also known as LiDAR.